Good morning. Today I want to go through Chapter 3, and I also want to review the problems that we had at the end of Chapter 2. And I also want to talk to you a little bit about the options of how you can proceed with the programming in this course. So there are a number of options. I've given you some of them already. The PLC Doodle is one. The Codesys is one. And then yesterday I got the ability to do a 21-day license with Simulator from Siemens for free. Now, there's nothing wrong with any of these approaches, and they all lead to a result that is probably okay. The way that I'm going to proceed is with the online one that, or the one that actually has the equipment in your hands, and it's a little bit more money. It's $189 plus a $20 for a power supply. Don't buy the Siemens power supply. Buy the $20 power supply that I recommended from Amazon. But if you do that, then you have a programmable controller that you can use for whatever purpose you want. I would recommend the TTL, or excuse me, the DC version. If you want to control 110 volt lights or something like that, you would opt for the other one, the DC relay version. But I think for a hobbyist, unless you want to play around with 110 volts, I would just use the DC version of the programmable controller. And that's the way the book is set up. And right now, the book is set up for the 1214 programmable controller. They've recently come out with a 1215 programmable controller, which is the one that they're recommending that you buy. It does not need to have the separate analog output. That analog output is built in, and I'm going to be going through and modifying my text to address that, and I'll address that as we go through this. But there's sort of subtle changes in the what we've had and what we're moving toward with this kit. That said, it's a nice device, and you're buying it at about a third the price that most people would be buying it at. And it's what would actually go into a control panel in a factory. So I guess someday, if you wanted to, you could actually put it in a factory environment or whatever. You're not supposed to, because it's supposed to be only for student use. But that said, I think it's a very nice way of learning. And at the end of the day, the $200 that you're spending for it is, I think, money well spent. But again, I'm not going to tell you exactly which way to go. And if you get to the end of the 21 days, they say there will be another round of the flyer that you can actually then do another 21 days, and that should get you at least part of the way through the semester that way. So I'm happy to help you in any way I can. And if two of you want to go together, and if you know another person and you can buy it, or however you want to do it, it's up to you. I'm not trying to say which way I would go if I were you, but on the other hand, I want you to understand that any of these approaches are acceptable, especially today. And I'm not going to grade down on one versus the other. So we'll talk about how I want things handed in, and we'll go through that as we go. Okay. So what is this PLC idea? Well, it's the same thing as what we talked about in chapters 1 and 2, except for the fact that now you're simulating on a computer the actual relay logic that you developed, or that you saw that was developed in chapter 2 with relays. So the whole idea, as it started out, was a replacement for relays, timers, and counters. That said, it's a computer. It can do anything that you can program, and it's sequential in nature, and with that you can do a lot more than you could with just straight old relays. So relays are asynchronous, so basically you cannot control the speed at which one versus the other turns on, so you can't do the sequential nature of programming like you can with a computer. So you can use the programmable controller to do a lot of things, and it can be useful for any kind of control, and it's especially useful for factory floor applications. It's a graphical language, so basically you're learning a programming language is what you're learning. And that said, it's gonna be eye-opening to you. So the fellow who will be emailing you, his name is Derek Bolton, and he is with Electromatic, and they're located in Detroit and also in Cleveland. They are one of 2 electrical distributors that cover the Northwest Ohio area, and I chose him because I work with him very quickly and very easily, and things tend to we can get this done. So they worked with us, and so the Studica thing went away. Studica wasn't willing to break down a 6-pack into a single processor and sell individual ones. The Electromatic will, and so they order them in groups of 6, and they break them down and send to each individual person and as an individual. So that's going to be an Electromatic part number, and they're going to be sending this out. So kind of a nice thing to be able to say that you're in the first group of people that potentially would be taking a course online, but yet with a lot of hands-on and very interesting capabilities. So with that said, let's just go through and look what a PLC is. So there's a CPU in the PLC, just like there is in the computer, and there's inputs and there's outputs, and we show that with the picture right here. Simple, very, very simple picture. Here is a little bit more sophisticated picture of the same thing. You say, well, why can't I just use an Arduino? Why can't I use a Raspberry Pi? Why can't I use a Linux-based system? Well, the fact is you can. The problem with most of those systems is they can go down easily, and they can not have it can happen in a way that you may not be able to predict, and it may happen in a way that might cause harm. Whereas program controllers have things built into them that protect you from having a problem that can cause harm to a person in a factory, or to the product, or to the machine, or whatever. So it's a little bit more sophisticated than just a computer. It's got things built into it. One is a watchdog timer, so that if you don't get through the program in a certain amount of time, it'll shut down. It'll shut down in an orderly way. Another one is the predictability of if you have a math error, or if there's something that causes the thing to fly off into Never Never Land. In other words, you lose your program counter. What happened? What do you do? Well, most systems just shut down, but you don't know where the I/O, what the outputs are going to turn on or turn off. You don't know what's going to happen, but you can not just predict those things, but you can control those things with a program controller. You can say the output stays in its last state, or the output turns off. You have that choice, and you can guarantee that that is a choice that you can have, and it does. It turns off the outputs, or it does whatever you tell it to do. And those are programmable things that you need to have control of, and you do. So it's not an expensive way. It's a way of putting a program controller is a way of maybe letting a second person, maybe an electrician, maybe a technician, maybe another engineer, look over your shoulder and be able to understand what you did. It's fairly simple in many ways, but in other ways it's very sophisticated, so that you can have very sophisticated things and not so sophisticated things running together, and they can all make a process run. And you can go very, very, very sophisticated. You can go very, 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 very simple. But whichever way you go, it's a way of controlling a machine or controlling a process. And so PLCs have not only expanded, they've basically taken over in the area of many areas of control. And you say, well, what about the codesys approach? Well, again, codesys is there, and if you want to use codesys, you can. But what do people pay for? What do people expect from you when you go out into the real world. You say, well, I've programmed an Allen Bradley. I've made these programs work. There is no proficiency test for programming of programmable controllers. There are some, but I don't know their value. There is no proficiency test that says you're proficient at X, Y, and Z. But if you can take with you to an interview a portfolio of programs that you have written that you understand, and you can talk intelligently in an interview with a potential employer about what you have done, that goes a long way to convince the employer that you're worthy and that you're worth hiring. So my emphasis here is one of you learning and then being able to convey that, what you've learned, to an employer. This is an important part of your process in getting to be employed, is being able to convey to an employer what it is that you understand. If you mention the word Allen Bradley, you'll get a look. If you mention the word Siemens, you'll definitely get a look, because most people are not, they don't know Siemens as well as they do Allen Bradley. So again, you say, I've looked at Allen Bradley, I understand it, but I was trained on Siemens. They'll train you on Allen Bradley, or they'll train you on their product. If it's a Japanese transplant, it's Mitsubishi or Omron. If it's an old style plant, sometimes it's Modicon or the Square D. Some people still use GE, but between, I showed you in chapter 1 the world acceptance of various PLCs, and Siemens is number 1, Allen Bradley is number 2, and everybody else is way down the list. So again, that's why we're doing what we're doing. So what happens in electrical circuitry? This is a very simple circuit. We have a lamp, we have a switch, we have a battery. What do we do with those? Well, you connect them, don't you? You connect the battery to the light through a switch and back to the battery. You have a completed loop. That's Kirchhoff's voltage law. Okay? Now, what happens? Nothing until you close a switch. When you close a switch, you get flow. And that's a control circuit. There's a very simple control circuit, but that's a control circuit. So we show that as a schematic. We can show that as a schematic. Now I want to take that same circuit and put it in a programmable controller. How do I do that? Well, I take the input from that and I put it to an input terminal block. And those terminal blocks are screw terminals, or they're terminals on the programmable controller itself. I wire the output. I wire the output to the output of the PLC. And what do I do inside? Inside the programmable controller, I take a program. I call this the world's simplest PLC. So here is my input, and here is my light. So what do I do to connect the two? I connect the two in software, and I do it through programming of a contact to a coil inside the programmable controller. This is not hardwired. This is inside, and you program this logic inside. Okay, so there's a LED for the run. You have to be in the run mode, and you see the input. When the input is pushed, there's a green indicator on the internal logic for the input. So when you push the input, you see a green LED turns on. And then when you turn on the program and the program is in the run mode, the output turns on and the green LED for the output turns on. And why do I use Q for the output? Good question. Well, you have two choices. You have an O or a Q. Allen Bradley uses the O, Siemens uses the Q. So I decided to use the Q. The Q is obviously a little different, but it's like an O, but except it cannot be mistaken for a 0. So they used the Q instead of the O for an output. So I came up with a generic nomenclature for the output, but there it is. Output Q number 0. So this would be my first output, output 0. Okay, so that gets you the world's simplest PLC. So how is the program processed in the PLC? First of all, the status of the programmable controller is uh, transferred from the process image table of the outputs to the output terminals. Okay, that's the first thing. Don't worry about that. Okay, so then you look at the inputs, and then you store them. Then you run through the program. Each of the program statements is executed, and then you go through the the last step, which is the fourth step here, and then you come to the point where you go back and you do it again. When we turn to item number 1, where you set the outputs. Okay, now this is a picture from Siemens. So you look at the inputs, you execute the instructions, first instruction, second instruction, third instruction, fourth instruction, and then you set the program to the outputs, and that's how it's done, and it does it in order. Now we need to talk about I/O. Don't worry about the scanning of the program controller. You'll see it again and again and again, but we talk about it. But it happens very fast. Happens about every 5 milliseconds, or more often. So it's a very quick and done situation. So again, it's very quick. Okay. Now we need to talk about I/O. We're going to talk about I/O through the whole book, but here we're going to talk about specific digital I/O, and we're just going to talk about it generically. What is an input or an output? Okay, inputs are defined, and you'll see me quoting this book, Liptak's Process Control book. It's a big fat book, and if you ever get a chance to buy a copy of it, do. It's old, but it's very valuable and very valid. And even though it may be a little bit dated, it still gives a lot of good information. And there's a lot of definitions in that book that I pulled out and I quote in this text. So again, what is an input? Well, here it is. It's real-world signals, and we're going to talk about different types. The analog or digital, lower high frequency, maintained or momentary, and they go to the program controller at a varying voltage, current, or resistance value. You can have either digital or analog, and here's a listing of some of them. Lots of different types of inputs. Here's a simple input. It's a switch. It's a limit switch, and you push this arm, and this switch will change position. In other words, something hits this, a package going down a line hits this limit switch, and it changes position. Outputs. There are 3 kinds of outputs: discrete, register, and analog. Don't worry about these kinds of definitions other than the fact that they're just there. So you have different types of outputs. Most of them are going to be digital. So what kind of things are you going to turning on and off? Pilot lights, solenoids, annunciator boxes, that type of thing. You can have analog outputs that drive speed signals and that type of thing. All kinds of things that you're going to do with outputs. Okay, so what are you going to worry about with outputs? AC or DC, 50 or 60 hertz, isolated or common source, true high or true low for DC. And this is a biggie for outputs, because with signals you always have to worry about with AC, just is it on or off? But with DC, is it a true high or true low? You have to worry about that, and you have to take that into account. All kinds of things. This is a solenoid. 2-wire signal turns on, it'll let the water flow through, turns off, the water stops. So this is a simple solenoid for liquid flow. Here's another one. You probably didn't realize that relays could be used as outputs, but they can. So with this, I can turn on this relay, and now I get 8 different things I can do with this. Some of them are signals that go to other processors or other devices, but this is a way of multiplying my signal and giving me many things that I can do. So this would be an output. Can very easily be an output. So what is this? Well, it looks like a button, doesn't it? Push button. Well, it also looks like a light, doesn't it? You can have a light in there, and you do. So, what is it? It's both. They're two independent devices. And if you want to, you can say, you can tie them together and you push the button and the light comes on. You can do that if you want to. But you don't have to. You can make it so that you push the button and something else happens, and then sometime later maybe a light comes on. They're two devices in one. This is an illuminated push button, and you can use it as such. Today it's a push button. Tomorrow it's a pilot light, or an output for a light, for a source. It's totally up to you what you want to use it for. You can make it blink, you can make it stay on steady, blink it fast, blink it slow, all kinds of things you can do with that. And that's exactly what we do with that, okay? Now, here is a first cut at a way of documenting your I/O. You have to do this. You have to document your I/O. And you'll notice that in the labs that we do, there is no listing of you have to do this to this. You have to tie this input to this terminal block. I don't tell you that. I give you the flexibility to do that yourself. Why do I do that? Because I want you to have to decide how you tie these inputs and outputs to the terminal blocks. And everybody's going to do it a little differently. You might tie it to the 0, 1, 2, 3. Somebody else might tie it to 2, 3, 4, and somebody else might tie it to 7, 8, 9, or whatever. It doesn't matter. If you make it work, it's okay. But this is something that you have to document. And you have to document it with some kind of a spreadsheet or a table. And I've seen spreadsheets that go 3 or 4 across, 3 or 4, like 30 or 40 things that you need to know about these inputs or outputs. Like, has it been bought? How much was it? What's the purchase order number? Is it on site? Is it installed? Those are all things that you might include in a spreadsheet. And there's people that's what they end up doing in most construction jobs. The person that he or she is they are a very organized person, and they keep track of everything, and they keep track of it in a spreadsheet. This is a very simplified spreadsheet, but this is mostly for programming. It tells you what the device is, it tells you what its function is, and then it tells you a signal assignment. Now, what does the signal assignment tell you? Well, it tells you whether it's normally open or normally closed. Normally open is a 1, normally closed is a 0. That's the definition of normally open, normally closed. Or you can just say NC, NO. Doesn't matter to me. But you need to have some idea of which way this switch is going to go. Now, in the United States, it doesn't matter too much. It does matter to a point that if you have something that overflows or causes a problem, if a wire were to fall off, that you would have it documented accordingly, and it's in the right position, NO or NC. In Europe, there's a law that says that you have to define these, and that if you don't do that, or if you do it in the wrong way, you can go to jail. So this signal assignment is a very important concept that the Europeans take very, 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 very seriously. In the United States, we take it seriously, but basically in the United States, we take it seriously because if you have a problem, you can get sued. In Europe, they will take you and put you in jail, supposedly. I've not heard anybody going to jail for this, but this is what they say. So again, the signal assignment, especially for inputs, is extremely important. I have been told by people that have been taking classes from me that if you ship a program to Europe, or if you ship a machine to Europe, you have to take all the inputs one by one and tie them both high and low and see if your machine program fails. Then you have to do it for all your outputs. Tie them high, tie them low, and then ship the documentation for this testing along with your machine so that if there is a problem, they can say, we have the proper documentation. It shows that these devices work with this program. So again, I don't want to belabor this, but you need to be aware of the fact that the signal assignment, while most of the time we really don't care, sometimes we care a little bit, it can be an important thing, and in fact, it can be very important. Um, so most signal assignments for the outputs are ones. If you turn it on, you want the thing to run. If you turn it off, you want the thing to stop running. That's very important. Most signal assignments for outputs are ones. Most signal assignments for inputs, you have to ask the question, if a wire falls off, can something bad happen? If it can, maybe I should go the other way. There may be something bad can happen that way as well. So again, you have to weigh the two, and you have to pick the best the two. So how do you make things run? How do you where do you start? Well, the whole goal of this class is to get you over the fear of starting. I've taught for a number of years, and the goal of the class is to get you to a point where you don't have any fear of starting with a blank piece of paper or a blank screen and start a program and get something on there that will actually work or kind of work, and then you go from there. Most programs don't work the first time. I hate to disappoint you, but there's going to be a back and forth with using the debugger, the program to get it to work, and it's going to take time. You say, well, that doesn't sound very nice. Well, it's why they pay you. This is not an easy process. This is hard, so it takes time. I was working on a project in Arkansas City, Kansas, and it was a project that we were supposed to get the information from a cattle rendering plant where the cattle were being slaughtered and they were coming through, and we were taking the information and reporting it back through a computer system as to where the cow was and what was going on and all that kind of stuff. Well, there was one weekend where on a Friday afternoon, the guy that I was working for said that by Monday we're supposed to be able to do this specific job, get the scale system to work. And I had not heard about it before. I just heard about it that day, and the guy that had written the program was going to go home for the weekend, so he's going to go back to Toledo. So we were stuck there, this other fellow and I, and they brought the scale system. The people from the plant brought the scale system in, and they set it there, and they found a problem, and they said, "Wow, we're glad we found that problem, so you guys don't have to worry about it." And I commented to the fellow that I was working with. I said, you know, that's the first of about 3 or 4 problems we're going to find in the course of the next few days before we get this thing up and running. And sure enough, over the course of the weekend, even on Sunday afternoon, we were finding more and more and more things that were wrong that we had to correct. So that Monday morning at 6 o'clock or 7 o'clock, we would be ready for them to accept boxes of beef down this line. Well, on Monday morning at 6 o'clock or 7 o'clock, here came those boxes of beef down the line. And in the process of that day, we ended up finding out that the time duration between when one box and the next box came down the line had to be 4 or 5 seconds. And the other person and I that was working down in the where the boxes were, we realized that boxes were coming faster than that. So for the first half day or so, we were getting a box if it came too fast. If there was not a 4-second gap, we were grabbing the box, putting it off to the side, waiting a little bit, and then feeding it through. And we finally got that down and working, and we actually, by noon or 1 o'clock in the afternoon, had a pretty smooth system. We got it down to 2 seconds and actually were able to feed all the boxes through. If you ever saw the old I Love Lucy film where they were bringing pies down the line, and Lucille Ball and her friend were trying to keep these pies working or whatever, and they were stacking pies all over the place. That's exactly how we were that morning. But my point is this: if we hadn't have gone through and done all that we had done prior to that, we wouldn't have even been to the state where we could have accepted the boxes that day. And that was a big deal because that was something that if we'd have failed at, the project would have been in dire jeopardy. So we got through it. We did what we had to do, barely, but we made it, and we were able to proceed, and we got through it very well. So again, I'm telling you that you think, oh, that's just that one problem. No, they usually come in groups, and they usually take a lot of time. That said, uh, this is, I hate to use the word fun, but you can have a great sense of accomplishment once you've done something like that, because you know that you've done something that is very hard and not many people can do. So, and people pay very, very well for that kind of thing. So you need to understand that this is not a simple project or simple process. In most cases, it takes time and takes energy, but you can learn and you can do this. And I want to convince you that you can. Okay, so you create a project, you configure the controller, you are the inputs, you have the ladder logic, you download it to the controller, and then you troubleshoot, and you troubleshoot, and you troubleshoot until you get it done. You keep this going until you're done. The hard part about this is it's hard to predict how long it will take to do some of these things. Sometimes you can predict, sometimes you can't. It's not always easy, but you can try, and that's where most of it's hard to do. But anyway, it's what you'll be asked to do. This is the Siemens processor. This is the Siemens S7-1200 processor. This is what yours will look like. There's not a power supply hooked to yours, so this you will have the little Amazon part. But anyway, that's neither here nor there. But that's what yours will look like. And this is the 1214. Now this window right here is not on the 1215. This was an add-on, and we don't do that anymore. We have the analog signal separate. Okay. That's the separate analog signal board for an output, and they don't do that anymore. Now we do not have these memory cards, but in the real world, you will probably you will use these because this is your backup of your program. So if your program dies or whatever, this is what actually goes in and retransmits the program down. So again, that goes in this little slot right here. We don't worry about that. Now what I would do is when you get your processor, if you do get a processor, these little covers, they do come off, and I just take them off. And I'm not saying that they're waste, but they are a waste. Okay. Now this was the L23 programmable controller that was the center of the Allen Bradley system until 3 or 4 years ago. And this was a processor that it had digital in, digital out, 24 volts, analog in, analog out, and it also had pulsed inputs. So it was a very useful processor, but it went obsolete almost as soon as we bought it, and it was kind of frustrating because even though it's the same processor, okay, the CompactLogix line of Allen Bradley includes CompactLogix, ControlLogix, and a number of others. It's the same programming language. It looks and feels like the same programming language. That said, CompactLogix processors are a little bit less expensive, and you'd call this a brick processor because it's all in one. You look at it and all the inputs and outputs are right there, and that's like a brick. So that's what that is called. But again, that one we've got them still, but they're not in use right now. This one is the one that if you were here in class, you would be using. This is an L16. So this one replaced this one, except for the fact that you don't have analog. So you have digital. You have 16 digital in, 16 digital out, and away you go. So this would be the way that you would do that. Now, what is this device? This is your power supply. This would be a power supply like you would have on a rack here at the university. 110 volts in, 24 volts out. What is this? This is a simple Ethernet switch so that you could bring your cable in to here, then have a short cable that goes out to the Siemens, another short cable that goes out to the Allen Bradley, and you never have to switch cables that way. This is, even though it's powered 24 volts, is a simple Ethernet switch that really you don't need if you go from your computer straight into Ethernet to either the Siemens or the Allen Bradley. You don't need this, but it's just there in case you did want to have everything hooked up all at the same time, everything talking. Okay. So this is the characteristics of this Allen Bradley. And then we talk about networking. So simple networking is just from the Ethernet port on the back of the computer to the Ethernet port on either the Siemens or the Allen Bradley. And we talk about the MAC address. Each of these devices have a MAC address, which you don't really get into. And then we also talk about the IP address. So the IP address typically for these processors is 198.162.0 and then a number. So we're going to talk about those numbers. And this is just theoretical stuff, but again, when you get these, it's going to be 192.168.0 and then a number. Now, here in the university, we have adopted a standard that the computer is 2. The Siemens is 3 and the Allen Bradley is 4. You don't have to do that if you don't want to, but the bad thing about the thing you can't do is have the computer and the PLC have the exact same address, because they won't talk if you do. So if you have this one at 01 and you load this one as 01, they'll stop talking and you can't get them back. So you have to change your IP address here on the computer if that happens. So basically, you can do whatever you want for IP addresses. My recommendation is stay away from 01. That's the PLC for the Siemens processor. Make it something other than 01. Make it 03 or 04 or whatever. But make your computer 0 and 2, and you have to figure out how to do that on your own. Okay, so on your to get this, now there's about 3 or 4 ways to start programming the PLC, and you have to download the software obviously to your computer, and we talk about that in here. We talk about it in a video, and the video is a little dated because we talk about IP addresses a little bit off, and that's okay, that's not a problem, but you just have to bear up with the idea of what I just said about the IP addresses. But this is where you start. Now this is the TIA version, whatever your version is. It won't be version 11, it'll be 14, 15, or maybe even 16. I don't know what you're going to be getting, but it's going to be something later than version 11. But this is the thing that's going to be on your desktop that you're going to click on to start programming the processor. So what is TIA? Well, totally integrated automation is what that stands for. And Siemens has put the complaint about Siemens over the years is extremely difficult to program. So they had a programming language called Step 7. Step 7 was their programming language, and they had a programming way of doing it, and it worked for them. But to sell it outside of Germany, they had a hard time. And the knock on Siemens always was that their programming language was extremely hard to use outside of Germany. So they endeavored to break that, and they have put a lot of money into this TIA software, a lot of money. Now, you'd say, what is a lot of money? Well, 4 or 5 years ago, I talked to the salesman from Siemens who covered this area at the time, and he said that at that time they put $1 billion into development of the TIA software. It looks like it. It's extremely flexible. It does everything that they want it to do, which is basically it covers all the major areas of automation. Other than robotics, it covers the HMI program, the coordinating with motors and drives, servos, all that. And it can do all that. It can control and talk to any of those things. So this is a very, very, very powerful package, and everything is included in the one package. And you can look at it and say, wow, that's very, very, very good. And it's forced Allen Bradley to have to do some of the same things. But again, there's good and bad about tying everything into one package. The bad side is obviously that you have to have coordination, because how many people can be working on the same thing at the same time? You have to have that ability. If you have multiple PLCs in your process and they're all working on the same programming platform, you have to have the ability to share information, but yet make it so that one person can't clobber another. So the coordination between people is extremely intricate. It has to be that way. And that's the hard part of any of this, is how do you coordinate it so that person A and person B doesn't mess with each other, but on the other hand, they can share information and go forward. And that they can create graphic screens. Many times there's one person programming the computer, or for the PLC, excuse me, for the automation and working on making the machine run. And you have a second person that is programming the graphics for the operators to be able to see. That is a very involved process where two people are working closely together, but one is working on one aspect, one is working on the other. And as they're doing this, they're trying to make both sides work well together, but you have two people working on the same programming package. And that's, again, intricate, and you're talking back and forth between two different people, different situations, and it's very hard to understand exactly how that all works. And I'm not trying to tell you every little piece about how that works, but again, this is a big package. It's huge, and it can do all that stuff. That said, you're just going to get a peek under the hood, and you're going to understand how the basics work. So you're going to understand the basic, how to program a PLC, how to program an HMI. We don't get into the drives at all, but they're there. So you're going to get into some of the parts and pieces of it. You will, perhaps one of these days, we may have a drive that we can hook to this thing, but we don't have that today. So again, this is how you start. This is called the portal view, and you create projects there. And we're going to go ahead and we're going to then go switch to the Allen Bradley. Okay, so this is the beginning of the Allen Bradley. Now, before the Allen Bradley can actually run, you have to do a program called RS-Links. RS-Links allows the communication of the computer to various programmable controllers, and that's this program right here. RS-Links Classic is this program right here, and you have two choices. You have either Ethernet or Ethernet IP, and either one will work. What is the difference? Ethernet IP is a little bit more of a brand-specific thing with Allen Bradley. It works with Allen Bradley. It's Ethernet, but it's brand-specific, and it works a little bit better than Ethernet. But either one works. You can do it either way. But you get this established communication, and then you click on this little button right here called the Who, RS Who, and then it shows you all the devices that are on that network. You can see every device that is on that network, and you can see your programmable controller here. And you can go down, you can drill down, and you can actually see your programmable controller running. Okay, then you get this screen when you start Studio 5000. You get to this screen, and then you click on I want a L23 or I want an L16. You click that, you set it up which one you want. This is the older L23. And then you get to this screen right here. Now you want to, in this screen right here, you want to go to main program. That's your blank piece of paper, and that's where you want to start. And once you've done that, main routine, you get this screen right here. And this screen right here allows you to start doing programming in this area right over here. Normally open, normally closed contacts, coils. They don't use a closed O, they use a bracketed O for the coils, but the coils are located over here, and that's how you start. Okay, now you say, Professor Evans, how do I do this? Well, we now have the capability, or I have at the end of the website, I have a program that does the startup of a Siemens and the startup of an Allen Bradley, and I'll show you that at the end of chapter 4. What else must you do? You must wire these devices. You must wire these puppies to get them to work. So if you are if you have a kit, a wiring kit of some kind with some wire in it, makes it very easy, but you have to wire the L to the plus 24 and the M to the 0 volts. Okay, so that's imperative. And now this is for the 1214. I don't have a wiring diagram for the 1215 yet, but I will work on that. But now, once you've done that, out here is a second L and a second M. So what they do is they tie this L internally to this L and this M to this M. What must you do? Well, you can use this for your 24 volts if you want to. And you can push a button and then you will turn on that input right there. But you must connect the M to the 1M right here. You must do that. So this gives you your 0 reference to this signal right here. If you don't do this little jumper right here, it ain't going to work. So when I push this button, I get a green LED with the O2, the I0.2 input, and I see that input, the I0.2 input in my program controller, just like I did before with that generic PLC. I will see that input turn on in my program when I'm running my program in the run mode. So how do I tie to an output device? Well, you have to tie the L and the M to this L and M up here. So you have to run up here, you have to run here. Now with this, an output, all you have to worry about is this, when the output turns on, this turns to 24 volts. Turns on a light or whatever you want to turn on. As far as I'm concerned right now, if you see the light here, you're good to go. You don't have to turn on an external light. But here's your 0 reference, back to 0, there you go. The older L23E, this is this wiring diagram for. That's that one. Here is the newer wiring diagram for the L16. This is the one we have upstairs in the lab right now. Okay, so now you have to worry about the run mode. You have to put the processor in the run mode. When you download, most of the time it asks you, either Allen Bradley or Siemens, do you want to go to run mode? And you say yes. With Siemens, it's run or stop. With Allen Bradley, it's run or program. Program mode turns off the run. There is, in both cases, there is a test mode, which I traditionally have ignored because I just let it run. You get it in a run mode, let it run. Test mode, you have to single step through the program. I've not used that, and I'm not familiar with that. You can use that if you want to, but basically I choose not to. So in the Siemens, if it's amber, it's not running, it's stopped. If it's green, it's running. That's what you want. Right there, that's the run mode. You want that run. Okay. Now we talk about, in different programming languages, upload and download. And if you have an Arduino, an upload is from the computer to the Arduino. It's just the reverse of that in programmable controllers. In a programmable controller, picture yourself on a mezzanine up above and looking down at a computer or at a machine. So you're up here on a high level and you're looking down at the machine on the floor of the factory. So you're up high in a control room, you're looking down. So to download, I take the program from the computer and stuff it into the program controller. If I upload, I'm uploading from the program controller to the computer. So you have the program in two places. You have it in the computer as you're writing the program and as you're debugging the program, and then you have the program on the factory floor in the PLC itself. So download to the program controller, upload from the program controller to the computer. And you sometimes must do both. So again, that's something that you must learn. This is the oldest programmable controller programming panel that I know of. This is the old Modicon 084 programming panel, and I programmed one of these. It wasn't for very long, but I did program one of these, and they're very crude, but they worked. And this was something that if you ever programmed one of these, you would never forget it. The very first thing you learned was you were flipping through addressing switches with thumb wheels and setting signals with thumb wheel switches. And after a while, doing that for a very long period of time, you got very good at setting those up and pushing buttons. This is a push button and thumb wheel switch setup. You got calloused fingers is what you did. Very quickly you learned that that's what you would have. The other thing about this is, how did you save the program? Well, they did not have a tape deck or a tape loader that you could use to save the program to. So what you had to do was, they had a modem, and you'd have a phone line, and you would call up their computer center in Andover, Massachusetts, and say, I want to save the program for XYZ controller, and they would say, okay, ready to go to data? And they would say the word data, D-A-T-A-R, as the word data, because they were from Massachusetts. And you'd say, ready to go to data. And then you would put the phone into the modem, and then you would see the red light turn green, and when it turned back the other way, or green to red, I don't remember which, but it would turn back and say, you're done. And you'd talk to the guy, and they'd say, yep, we got it. And that would be, they would save the program to a tape drive on their master computer back in Andover, Massachusetts. And that's how the programs were saved for a long time. For at least 5 to 7 years, they had that capability, and they finally got rid of it because they came out with their own tape program. But that was one of the ways that people ran programs for quite a while, was go to data. And that's how you programmed it right there. Kind of odd, but that's how it was done. Okay, so I'm not going to redraw this, but chapter 3, problem number 1, to connect to a specific input, what you have to do is you have to do the M to the M. You have to do the M to the 1M right next to it. And then you have to take an L, either one, and go to your switch. Here's a normally open limit switch. And then you go to your specific point. Like if it says I 1.4, it's over here, 1.4, and you would go all the way over to there, and that would be your tie point. For an output, so this is for an input, a discrete input, a DI, digital input. For an output, you have to tie the L to the L up there, so the L has to be tied to the L, the M has to be tied to an M up there. So you have to give it a reference, and then the output point is 1.0, which is Q 1.0. Out here, you go to your device, you go to your solenoid, and then you go to tie the other side to the output, or the 0 volts of M. So here's my solenoid. So that would be the answer to number 1. Number 2. So for the L23, which is, we've obsoleted these, but for the L23, you would have a input that goes from a plus 24 someplace to my discrete input. If I say go to data point 3, I would go to point 3. Data point 3, dot 3. And then I would also tie my common to my 0 volts. And that would be it. The output, I have a plus DC, I have a plus 24 on my card. I have to go from there to my plus 24, hit that. I have a DC common, which is down here. Which I have to go to the 0 volts. And then I have my output. Again, my output goes to the solenoid, and from the solenoid to the to the 0 volts. So basically, this is a true high signal, and I would go from my output, whichever one it is, data point 2, 0.2, and I would tie that point then to my 0, and I'm done. So that gives me an answer for, in general, to the Allen Bradley solutions. Okay. So also in this chapter we talked about the original Modicon 084, and the point of the original Modicon 084 was what? The first input could either be normally open, normally closed, and then all succeeding inputs could either be normally open or normally closed, but if they were ORed, they had to go all the way back to the original, to the bus at the left. So you could not build much circuitry that was very sophisticated other than you had to redesign circuitry. So basically you looked at a circuit and you redesigned it, is what you both basically did. So we're going to look at that. We're going to say, okay, with those rules in mind, how do you do these? So this was, if you were programming an old original Modicon 084, and I just gave some generic names, so what would you do? Well, one of the things you got to do is you got to remember that you can go to specific points. So let's go for number 3, N2 and N3, and then okay, so what I'm going to do here is I'm going to say N1 and okay, I'm going to do N2 and N3. I'm going to go to a point, let's just call it A. Okay, A. Now that gives me those two. And then those are ORed with the ORing of not N4 and output 0. So basically, those get ORed with N4 and output 0. Okay, so let's do that. N4 N4 not and output 0, and excuse me, and then we OR that with this. The next thing we do is we drop this OR function down here, which is this thing right here, which is the next one, which we call A, and that goes all the way back to here. So now we've done this part and done this part, and that we've got one more count here, so we can do this last one. We can flip it around the N1 and do it right here, and that gives me my output 0. So do you see what you have to do to circuits? You have to physically turn them around many ways, okay? Then the N4 and N5 go to output 7, you can leave alone. Output 0 and output 7 go to output 2, you can leave that alone as well. Number 4 is a little messy, but we can do this a number of ways, but one of the ways that you can do this is N1 or N2 go to A, N3 or N4 go to B, N5 and N6 go to C, and then A and B and C, I can AND them together, and that gives me another one, D. A and B and C go together, and that gives me another one called D. Then D and N7, or excuse me, I'm going to go this back. I'm going to do this the other way. You got to flip this logic around. It's N7, and then OR output 1 and D give me output 1. So it's kind of complicated, but that's how you did those in that era. So it gives you a little bit of practice with writing of logic, but having to turn it around and write it a little differently. As you look through this chapter, you're going to see some examples of what I would call helps that come along, and you usually stick these into chapters. But for instance, some of the things that we've found along the way, and this is on page 39 of chapter 3, are helps for setting up various PCs based on the rules that we found for this is the Siemens server, and also the Allen Bradley server, because we've set up servers to parse out the activation code so that a person can use the software. So some of this stuff that you're going to find at the end of some of these chapters is extra information for those who have been before you, that they needed this information, and we just put it in this book. So it's sort of there. You're going to find it at the end of some of the chapters, but just be aware of the fact that unless you're setting up a server with multiple seats, you're not going to need this. But if you do, here it is. We kind of went along with the rules of the road and tried to keep track of all this information, and the only place to stick it is in this book, so that's where it's at. So take care and have a good day.